Thank you for the introduction. Hello to everyone. I'm Medica Califano. I'm an associate researcher from the University of Salerno in the south of Italy. And today I'm going to show you some of the results we have obtained up to now about the fatigue strength of high-strength steel welded joints using local approaches, thanks even to the work of some students of ours. Just a very quick introduction. We all know that the 90% of fractures and failures are due to fatigue, but when tackling the issue of fatigue, we need to take into account that it has a multifaceted nature. So each fatigue analysis should take into account several aspects like the kind of material in play, environmental conditions, manufacturing technique. But one of the most important aspects is the geometry. So when we talk about components, or like for example joints, welded joints, the geometry plays a very important role, because we know that the welding toe, in case of welded joints, has two end root which act as notches. So the fatigue performance is influenced by the geometrical discontinuity represented by the welding toe, the fatigue behavior of the base material, and the local stress or strain field. That's why local approaches are appealing. They have always been used by scientists and researchers for this kind of problems, because they allow to take into account the local stress or strain fields that arise near the geometrical discontinuity represented by the welding bead. Concerning the local approaches, we focus on the strain energy density method and on the effective notch stress approach. So concerning the strain energy density method, we all know that it's based on evaluating the strain energy density in a control volume that is typically cylindrical, surrounding the notch. And we know that the critical failure condition is usually met when the strain energy density equals the critical strain energy density value. And here you can see an example that is available in literature of hundreds and hundreds of welded joints that were tested. And here we have the fatigue strain energy density versus number of cycles to failure. And what we notice is that there is a clear scatter band that is able to comprise most of the experimental results. Concerning the other approach, effective notch stress 1, this considers the macrogeometric effects which are related basically on the shape of components and the structural discontinuities that are related to the welding bead. In this case, the notch is not considered as a sharp edge, but is a blunt notch. So we introduce a reference radius that's even called the fixtures radius. Here you can see its expression that is available in literature. It's quite commonly used. And for steel, here we have the parameters that are usually used, but in general, this reference radius is of about 1 millimeter. So in this framework, as I anticipated, the aim of this work is evaluating the fatigue characteristics of welded joints, taking into account the geometrical criticalities which are intrinsically introduced by the welding bead. So now I will focus on the materials and methods, then I will show you the preliminary results and wrap up with the final conclusions. Just a few words about the materials and methods. I will briefly show you the case studies and then describe the different activities that have been carried out so far. So we have the first phase, that is a reverse engineering phase, that allowed us to reconstruct a high-fidelity numerical model able to catch all the geometrical characteristics of the actual welding bead, because we know that the geometrical features of the welding bead may vary along the welding width itself. Then we carried out some tomographies, computed tomographies for the detection of the geometrical parameters of the cross-section of the specimen in order to construct a numerical model and carry out a finite element analysis for the implementation of the local approaches. And finally, we carried out some experimental fatigue tests. Well, concerning the case studies, they are laser beam butt welded joints in high-strength steel. Here you can see the welding parameters and a schematic of the joint, from which the specimens, dot bone specimens, were cut out. We had 3 joints that were called A, B, and C. from each joint, 8 specimens were cut out. 7 specimens were used for the experimental test, while 1 specimen was used for the metallographic analysis. And here you can see example pictures of 2 specimens extracted from the joint B and joint C. Concerning the first phase, so the reverse engineering phase, each specimen was equipped with given markers. The specimens were positioned on a plate that was equipped with markers as well. Then we used a laser scanner, which is the FreeScan UE Pro, which is a small and portable scanner, which is quite easy to handle. And by scanning the specimens, we were able to acquire the points cloud. So we got this numerical model which need to be adjusted because there were some holes due to the presence of markers. So the numerical model was adjusted and a first mesh was created by means of the geometric RAW software. Then we focused on the central part of the specimen, so around the welding bead. And with cutting plates, we cut this volume in order to obtain all these curves that represented the section of the welding bead for the top and bottom surface of the specimen itself. So what we did basically was study the curve, so the section curve for the specimen near the welding bead, and we tried to evaluate these geometrical parameters that are summarized in this table. So we have the vertical misalignment, we have the height of the welding bead, we have the radii at the top, both left and right, the inclination angle, the welding bead's width, and the thickness of the specimen itself. So what we did was basically writing a Python code in an Anaconda environment, and it was a study function, we might say. So we studied the function that represented the section of the welding bead. We carried out some studies on the first derivative, second derivatives, convexity studies to catch all the important points that allowed us to compute the geometrical parameters. Now here we have the micrographs that were obtained through the computed tomography for the 3 joints, or specimens, sorry, extracted from the 3 joints, A, B, and C. We are able to highlight the fuse zone, the heat-affected zone, and the base material. And we can see how even, for example, for the specimen from joint C, there is a clear misalignment between the plates of the joint. Now, focusing, for example, on the specimen from joint B, by means of an image acquisition software, we were able to extract the main geometrical dimensions to construct this very simplified geometrical model. This geometrical model allowed us then to go on to the finite element model that was constructed for both the Sepe approach and the notch stress approach. Concerning the strain energy density approach, in this case, we know that the control volume need to be considered and so need to be meshed. In particular, according to literature, this control volume has a radius of 0.28 millimeters, and there are 8 elements along the radius according to literature. And here the notch is considered as it is, while as anticipated in the case of the notch stress approach, we have a blunt notch, so we consider a reference radius and a control radius, which is it is slightly larger. So the radius is 1 millimeter and the control radius is 1.1 millimeter. And so around the notch, we have an element size that is equal to R divided by 20, where R is the 1 millimeter radius. The load, the applied load was simply tensile load of 1 megapascal for reproducing the mode 1 loop beam. Then we carried out experimental tests. So first of all, static test for obtaining the stress strain curves. So here we have the mean curve for the 3 joints, A, B, and C. And here we have the mean values for the Young modulus and the maximum stress. Concerning the fatigue tests, they were tension compression fatigue tests, so we are equal to -1 with a frequency comprised between 5 and 10 hertz. And here you can see a picture of the specimen mounted into the instrument belonging to our lab and a picture of the same specimen after the end of the test. Now, going on to the results, we have the first results regarding the morphology of the welding bead. So I reported here again the curve that represents the section of the welding bead and the main geometrical parameters. For the sake of brevity here, I'm showing you just the geometrical parameters for the specimens from joint B, and in particular, these parameters are for the upper curve. And we may see how the most scattered parameters are the two radii for the two of the welding bead. So the left and right one, and even the height of the welding bead, and this result is quite expectable. Concerning the results for the finite element analysis, concerning in particular the set approach, here we can see a contour plot of the stress along the x direction, that is the horizontal one. And here we have a zoom in of the upper contour volume, and this is a contour plot of the strain energy in that volume, dividing the total strain energy by the total element volume. We have the strain energy density itself. Then, using this equation, which is quite famous in literature, we could compute the fatigue strain energy density values. So here we put the strain energy density coming from the finite element analysis. Here we have sigma F, which is the 1 megapascals that we applied for the simulation. Sigma AI is the stress amplitude for the height fatigue test, and here we have then the set values. Here we have the set values plotted versus the number of cycles of failure for the upper and lower contour volume of our specimens. We can see how some of data do not fall within the scatter band that is available in literature. Maybe this could be due to secondary effect that may be introduced during the fatigue test, as it is a tension compression test. Concerning the results for the notch stress approach, here we have again the meshed model, and here contour plot of the stress along the horizontal direction. And we computed a notch stress intensity factor of 1.45. And here we have the classical SN curves in terms of nominal stress amplitude and effective stress amplitude. So it's clear how the effective stress amplitude is shifted upwards. So in conclusion, we know that the fatigue performance of welded joints is connected to the geometrical features, and local approaches are useful to tackle this kind of problems. In this case, we analyzed the specimens extracted from butt welded joints obtained by laser welding. And these specimens were first of all scanned in order to reconstruct a high fidelity numerical model and evaluate geometrical parameters of welding bead. We carried out some very simple finite element analysis and some experimental tests in order to link in some way the experimental and numerical results. What we noticed is that the most scattered geometrical parameter is the toe radius, both left and right radii actually, which may represent the most influencing geometric discontinuity. In addition, there were some, let's say, correlation between the geometrical data that we evaluated through the reverse engineering and the ones that are usually used for example, the notch stress approach. But concerning future developments, what we should say is that, first of all, we would like to calibrate the numerical model. So taking into account the actual geometrical parameters that we evaluated through the reverse engineering. And then we would like to correlate the welding parameters to the geometrical features and then finally to the fatigue strength in order to be able maybe to predict the fatigue strength even for untested specimens. This is all from me, and I really thank you for your kind attention.